Today we're talking about logarithmic graphs. For the warm-up, you're going to graph the exponential function and you're going to then graph the inverse. So you can go ahead and do this without your graphing calculator, and when you pause the video, when you're done, you can unpause and check your work. So we know that f of x equals 2 to the power of x is an exponential function because it has the variable as an exponent. If I plug -1 in for x, we know that when we plug in negative values, in for an exponent, then that goes in the denominator, becomes positive when we simplify. So that means that this is equal to 1/2. Anything to 0 power is 1. This is 2, 4, 8, and 16. And then plot your points in graph, and your graph looks like this. And so for this graph, we know that the larger and larger x values that we plug in that are negative, the closer and closer to 0 our graph is going to get without actually hitting 0 on our graph, which means that we have what's called an asymptote. And recall that an asymptote is the line the graph approaches but does not touch or cross over. So we want to make sure to always include that on our graph when we're graphing these exponential equations. And so this is, of course, a horizontal asymptote at y equals 0. The domain for this function is all real numbers because we can plug any value in for x. The range, however, is from 0, not including 0, to infinity. For the inverse graph, we can take the x values from f of x, and those become the y values. So -1, 0, 1, 2, 3, and 4. And the y values become the x values. So 1/2, 1, 2, 4, 8, and 16. Then go ahead and graph. And so this would be my inverse graph. And for this, if we have a horizontal asymptote at y equals 0, then the inverse has a vertical asymptote at x equals 0. Because again, for inverses, you switch your y and your x values. So that's a vertical asymptote. The domain is now, you can see 0 to infinity. So we cannot take the log of a number that is 0 or negative, because remember that this inverse, we've talked about this before, is actually a logarithmic graph. And so the domain from our original function becomes the range, which you can see on the graph of our inverse. So let's just algebraically look at the inverse just to remind ourselves how to do it. So we have y equals 2 to the power of x. Remember, when you're finding the inverse, you switch your x and your y values. So this is x equals 2 to the power of y. And so we want to then next solve for y. So the question is, how do you solve for y when it's an exponent that's a variable? And so in order to do that, you can't take the y root, but we use logarithms. So the log and the base stays the base. So log base 2 of, and the argument is x, is equal to the exponent y. So this function over here is actually equal to log base 2 of x. So that's the inverse. For these, we can evaluate these without our calculator. So we're saying, remember that the argument 64, so that is the answer to the exponential form. So if we put this in exponential form, we're saying 2 to what power is equal to 64. So 6. This is 6 to what power equals 1 over 36. So remember that 1 over 36 we can rewrite as 6 to the -2 power, so -2, and 10 to what power equals 100,000. So that would be 10 to the power of 5. Now, for this, we can go ahead and start the task. We're going to construct tables of values to help us graph logarithmic functions. And of course, we always want to make sure we're graphing the entire graph. So be sure to select at least 2 values in the interval from 0 to 1 for x, because that gives you these values that we had up here that are approaching your asymptote. So we actually just graphed this equation of above, y equals the log base 2 of x, because we showed that that was the inverse of the exponential function. So I'm going to copy the tables below and put them down here. So recall that this was y equals 2 to the x. And why do we use base 2? Because this is base 2, so whatever the base is, if you were to rewrite this using the inverse and exponential form, you get y equals 2 to the power of x. So then you can use the inverse to help you graph the logarithmic function by switching those x and the y values. And again, do not use your calculator for these. So when you plot your equation, so this is the y equals log base 2 of x, plot those points, then you connect your values and get your graph. And again, I'm just going over this fast because we just did this above. And then you have, of course, your vertical asymptote at x equals 0. And so again, since the base of the log is 2, we're going to look for perfect squares. Because remember that the answer to a log is an exponent. So that's why it's helpful to think about exponential form, because of the fact that the answer to a log is an exponent, and that kind of helps you graph without your graphing calculator. So let's go ahead and look at another one that's not a base of 2. So for this one here, notice that the base is 3. So if the base is 3, we're going to think about perfect cubes in order to help us. So if you want to first find the inverse of this, so to find the inverse, you remember you switch your x and your y's. So this is log base 3 of y equals x. And then you would put this into exponential form. So you can do your loop trick if you need to. So 3 to the power of x equals y is the inverse. So I'm going to use this to help me graph my logarithmic function. So if I make my table, remember to include a value that's a fraction, and so that means we want to make sure we have a negative x value here, because that gives us fractions for y. So -1, let's do 0, 1, 2, and 3. If I plug -1 in, 3 to the -1 power is 1/3. 3 to the 0 power is 1. 3, 3 squared is 9, and 3 to the third is 27. So if I graph then the logarithmic function, so y equals log base 3 of x, I'm taking this table and switching my x and my y's. So 1/3 is -1. 1, 0, 3, 1, 9, 2, 27, and 3. So if we were to actually write that out, that would be the log base 3 of 1/3 equals -1. The log base 3 of 1 equals 0. The log base 3 of 3 is equal to 1, etc. And that's because of the exponential form. So 3 to the power of 1 is 3. 3 to the 0 power is 1. So that's what I'm talking about when I say to use the inverse to help you graph this. So we have 1/3 -1, 1, 0, 3, 1, 9, 2, and 27. 3 is not going to be in our graph. It's too far. So we're just going to graph our graph without that point. And I usually try to use the entire piece of graph. And then I want to include my asymptote, which is still at x equals 0. So we have a vertical asymptote at x equals 0. The domain, notice, is still going to be from 0 to infinity, not including 0. And the range is still all real numbers. And again, we looked for perfect cubes since the base of the log is 3. So again, the perfect cube, so the 3, the 9, 27, so these values. So let's go ahead to the next one. Log base 4 of x. So for this problem, notice the base is 4. So if you want to find the inverse, again, switch your x and y. So log base 4 of y equals x, because remember this is equal to y, so we switch them. Then we rewrite this in exponential form, so 4 to the power of x equals y. That is the inverse. And I can use then this to help me go ahead and graph the log. So let's do -1, 0, 1, 2, 3. And so for this, if we go ahead and plug this in, if I plug in 4 to the -1 power, so 4 to the -1 power is 1/4, because again, remember negative power means goes to the denominator. 4 to the 0 power is 1. 4 to the first is 4. 4 squared is 16. And 4 to the third is not going to be in our graph, so let's go ahead and we'll just stop at the 2. Now I want the inverse, so I would switch these values. So this is 1/4, -1, because the log base 4 of 1/4 is -1. 1, 0, because the log base 4 of 1 is 0. The log base 4 of 4 is 1, and the log base 4 of 16 is 2. So 1/4, -1, 1, 0, 4, 1, and 16, 2. And then go ahead and connect your values. And then don't forget to also graph your asymptote. So we have a vertical asymptote at x equals 0. Domain is still 0 to infinity. Range is still all real numbers, -infinity to infinity. Now, I don't always graph the inverse in order to help me graph my logarithmic function. So when you get better at this, you can just kind of think about the base and think about your, like I said, perfect squares or perfect cubes. In this case, we use the base 4 in order to come up with the values. So I knew that 4 to the first power and 4 squared is 16. So that's kind of another way you can look at it. So the next question says, what is the effect of changing the base on the graph of the logarithmic function? So it changes our output and our output values and makes the graph closer or further to the x-axis depending on what those values are. How do you predict the graphs of y equals the log of x plus a and y equals the log of x minus a will be different from the graph of y equals the log of x? Notice that this a is not on the inside, it's not part of the argument. Remember, the argument is what you're taking the log of. So this is not a part of the argument. So that means, what do we think is going to happen? I think that this graph right here, plus a, if it's on the outside, think about your quadratic function, think about your cubic function. What happens when you have a value on the outside? Think about the absolute value function that we did. This is going to move it up a. And what is this going to do? It's going to move it down a units. And so just as a note, the a value is on the outside of the argument. And remember that argument, what does that mean? It's what you're taking the log of. Or I should say the value. So what you're taking the log of, and in this case, both these are x. So we're going to test our prediction on the graph of y equals the log base 3 of x plus 2, comparing your graph in question number 5. So the parent graph is y equals log base 3 of x. So we can just use our table above in order to help us graph. So 1/3, -1, 1, 0, 3, 1, 9, 2. And notice that when we did our table, if the base is 3, you have 1/3 here. When it was 4, notice you have 1/4. When it was 2, notice you had 1/2. That will be the case for all of your logarithmic functions. And then also notice that we always have 1, 0, and then the base, comma, 1, and then we did the powers of whatever the base was, so that should help you graph. So when you're doing these graphs, you should always first graph the parent function, and then the second step would be to graph the transformations. So for this, the parent graph, we have 1/3, -1, 1, 0, 3, 1, and then 9, 2, and again, remember that's the next perfect cubed. So if we think about 3 to the third power, it's 27, but it wasn't on our graph. And so this was my parent graph, which has an asymptote here at x equals 0. And if I graph my transformed graph, we have +2, so that moves it up 2. So I just count up 2 from my parent graph. That's why it's nice to graph the parent graph, because then you can just move your graph from that. And the vertical asymptote did not change. It's still at x equals 0. The domain did not change. It's still 0 to infinity. And the range is still all real numbers, -infinity to infinity. Make sure you always use interval notation when writing that out. All right, so for the next one, it says, how do you predict the graphs of y equals the log of x plus a, and the log of x minus a will be different from the graph of y equals the log of x. So now notice that the x plus a and x minus a, the a is on the inside of the argument. So this one's going to move the graph how? So if it's on the inside, remember it's opposite thinking. So this moves left a units, and this one moves right a units. And so again, a is on the inside of the log. So it's a part of the argument now. That's how we know we're moving it left or right, versus where it was on the outside of the log, not a part of the argument, which is why it was moving up or down. So test your prediction on the graph y equals log base 4 of x minus 3. So the parent graph is y equals log base 4 of x. And then what are we doing to the parent graph? That minus 3 moves it to the right 3. So if we want to graph the parent graph, we're using a base of 4. So in my table, I could graph the inverse, but again, you should try to practice without having to graph that. So since the base is 4, I'm going to use 1/4. So log base 4 of 1/4 means 4 to what power gives us 1/4? 4 to the -1. Then the next value that I'm going to use is 1, and we know that's one of our properties. Log base 4 of 1 is 0 because 4 to the 0 power is 1. Again, the base is 4, so the next number I'm going to use is 4. So 4 to what power gives me 4? 1. And then think about your perfect squares. So 4 squared is 16, so log base 4 of 16 is 2. So we can go ahead and plot these points. 1/4, -1, 1, 0, 4, 1, and 16, 2. And again, if it helps you to actually use the inverse graph to graph this and make the table, that's perfectly okay. And then we can go ahead and now move this right 3. So if I move this right 3, that also moves my asymptote right 3. So 1, 2, 3 would be right here. And I'm going to move this point 1, 2, 3. Same thing with this point. All the points get moved 3 to the right. And then connect those values. And so when we moved it right 3, notice that changed my vertical asymptote. Now it's at x equals 3. The domain is also changed. Now it's from 3 to infinity, but the range still stayed all real numbers. So be careful when you're moving your graph right and left that you also move that asymptote on your graph. So for the next part, it says describe the transformation, state the domain and range, graph the following functions using different colors. So why don't you go ahead and graph all of these functions on your own, and when you're done, you can unpause the video to check your work. So we know this first one's just the parent graph, and we've already graphed this a few times. So again, if you want to make a table, you can. Hopefully by now you can kind of do without a table. So the base is 3, so I'm going to use 1/3, 1, 3, and then the next one would be 9, and then 27 was not going to be on here. Well, now it's on there, so 27. So this would be -1. Log base 3 of 1 is 0. Log base 3 of 3 is 1, 2, and 3. So on my graph, I would plot those 1/3, -1, 1, 0, 3, 1, 9, 2, and 27, 3. So you always want to use as much of the graph as you can when you're graphing it. So notice that's why I always go all the way over on my graph. Same thing when I go down, and then I have my vertical asymptote. So we're also going to include that here. So vertical asymptote is x equals 0. Domain is 0 to infinity, and the range is all real numbers. And in fact, the range for all of them will always be all real numbers. So I'm going to go ahead and just write that in. So the next one, what are we doing? We have to figure out what type of transformation we are making. If I look at this, I would ask myself, is that 2 on the inside of what I'm taking the log of? No. So that means it's not a part of the argument. That means this one's going to move up 2 from the parent. So from the parent, I go up 2. And then I can go ahead and connect the points. And notice that did not change my asymptote at all. So vertical asymptote is still at x equals 0, which then means the domain is still 0 to infinity. Looking at the next one, now notice that the 2 is on the inside of what I'm taking the log of. So since the 2 is on the inside of what I am taking the log of, that means this is going to move it left to right. In this case, it moves it to the left 2. So on my graph, that means I moved the asymptote left 2. And then every point gets moved to left 2. And that, of course, means that we've changed our domain and our vertical asymptote. So vertical asymptote is at x equals -2. That means the domain is -2 to infinity. For the last one, we have 2 different transformations that we are going to do to our graph. So for this one, we have the inside, which moves our graph to the right 3. And then we're going to move the one on the outside down 2. So right 3, and then down 2. And I'm just going to do both the transformations together, so because we already have a lot of graphs on here. So again, I start from the parent graph, which was the one in green. I'm going to move my graph right 2, so I have to move that asymptote right 2. And moving an asymptote up or down doesn't make a difference. So right 2, down 1, 2, 3. Or no, what was it? Right 3 and down 2, so we need to fix that. Sorry. Can I fix that asymptote? So right 3, so 1, 2, 3 be here. So vertical asymptote is at x equals 3, and then down 2. So right 3, down 2. This point goes right 3, down 2. And again, right 1, 2, 3, down 2. Again, we're using the graph in green, so right 3, down 2. and then connect those values. Sorry, that graph is a little hard to see. So I'm going to go ahead and use my highlighter to highlight it so you can see a little better that it's this graph right here. And this was the asymptote. And that would be all of my graphs graphed together. So the vertical asymptote is x equals 3, and the domain would be 3 to infinity. Now we're going to write equations given the graph of the logarithm. So for 12, it says write the equation for each of the following functions that are transformations of. So it's telling us that they're transformations of f of x equals log base 2 of x. So since the base is 2, you're going to think about your parent graph is the first thing that I would probably draw on my graph. So base 2 means we have 1/2 -1, 1, 0, 2, 1. What's the next perfect squared? 4. So 2 to what power gives us 4? 2 to the second power. Then the next one would be 8, 3, and 16, 4. So this is my parent graph, and I like to draw that because it's going to help me determine how my graph has moved. So how has my graph moved? If I take this graph, it looks like I've gone obviously to the left, and it looks like I've possibly moved it down, but it's hard to tell. So if I use this point right here, I always usually start with 1, 0. So if I take that point and go left 1, 2, 3, and let's take this point left 1, 2, 3, left 1, 2, 3. So it looks like I didn't move it up or down at all. I just moved my graph to the left 3, which means my asymptote is right here at x equals -3. So graph moved left 3. So what's the new equation that we have? Y equals log base 2 of x plus 3. What if they didn't give you this piece of information right here? How could you figure out what it is? You can kind of look at the graph and see, try to see if you can find this point right here, which was this point, and kind of go from there. Or you can even count how far you are. So usually that first point next to this one tells me what the value is going to be. So since it's right next to it, I know that was going to be here at base 2. We'll talk about that more later. So again, draw the parent graph. So 1/2 -1, 1, 0, 2, 1, 4, 2, 8, 3, 16, 4. So that is my parent graph. And how did my parent graph move? So I'm going to start with this point. So it moved right 1, 2, 3, and it's possibly right there. So let's check another point. Right 1, 2, 3. Down 1 would be there. So it can't be right 3 because then that next point does not fit. So we know it's not right 3. So let's try something else. So I'm going to try to see if I can find these 2 points together. Looks like maybe here and here. So let's try that. So if I go right 2, down 2, that works. This point, if I move it right 2, down 2, that works. What about this one? Right 2, down 2. And right 1, 2, down 2. So actually we're going right 2 and down 2. And so that means this is y equals log base 2 of x minus 2 is the right 2, and then down 2 is -2 on the outside of the argument. And that's it.